So far, what you've done the past 2 nights is really learn how to get any quadratic into this form. Okay, so once it's in this form, it's called vertex form because the two numbers there are the vertex. If I change h, that changes the x. Of course, if I change this to where it says minus 2, just know that goes to positive 2, not negative 2. It's not over here. So I know the vertex just by looking at the equation, and that makes it a lot easier and faster to graph. You guys also know how to plug in 0 into this. So I plugged in 0, I'd get what, 4 minus 5, which is negative 1, and you can see the y-intercept is at negative 1. So we can graph this pretty effectively when it's in this format. And we can also figure out these x-intercepts, which we're really going to move to this week, is where are these x-intercepts? Where does it cross the x-axis? And if this was an object that's being thrown up in the air, I make that a a negative. Think of this as an object being thrown up in the air. The intercepts are like, if this thing's thrown in the air, where is it taking off? The vertex is how high does it go, and the other intercept is where does it land. So think of the two of those as, something that actually has a meaning, not just, well, what are they? So the intercepts are starting and landing. The vertex is like how high in the air did it go, where you're throwing an object like a football or anything. Okay. Here's the thing. We also have these imaginary numbers. So what happens when we get something like this? It doesn't cross the x-axis. There are no real number roots. Okay. But we still have roots. Okay. So when we start getting like a vertex that's up here and the parabola does not cross the x-axis at all, we still get some roots. Okay? We get two complex roots that are actually right here and right here. And that's where they are. If I move them around, you can kind of see how the complex roots work. Notice how they're the same distance from 0. So there's one right here, there's one equally above and below. That's because whenever we do roots, we always get pairs of them, and it's always in the form of plus or minus. So it's like 0 plus or minus, so you get 0 plus and 0 minus. That's why we always get 2. There's one above, one below. Exactly. Okay. Now what do these roots mean? Okay. Has a meaning. Okay. We take those roots and we actually rotate them to the real side. There you go. So the imaginary or complex roots are actually the real roots if we flip this thing over. So if we just change the a and we flipped it upside down and we found the roots, the real roots of that, that's the same as the complex roots. Just rotate it a little bit. So there is a actual meaning of all these complex roots and what they do. Okay. Application-wise, complex roots or complex and this whole idea of the imaginary number I, it's used to calculate values or power that's flowing both directions. Have you guys ever heard of like AC current and DC current? Like electricity, like you plug in your phone and charge. It's charged by alternating current. There's two types of current, alternating and direct. So that's called AC and DC. Alternating current actually has current running in both directions at the same time. That's how you can hook up a solar panel, right, at a house, and the current, you can get charged, but also the dial on the house will run the other direction because there's power going out of the house because it's generating electricity. And when you have those, the government actually pays you for making electricity. So with the wires, the electricity can run both ways. You can bring it in to use it, but it can also go the other direction. So how do you calculate the power flow in both directions at the exact same time? Okay? That's where you get imaginary numbers. The real numbers is the direction of the electricity in one direction, and the imaginary numbers, which is not imaginary like fake, but there's also power running the other direction at the exact same time because it alternates, goes back and forth. So this is way anything that's electrical and like Southern California Edison workers, construction, and whatever, they use these instruments to measure, what's the current flow in both directions at the same time. One of those is actually imaginary numbers, and that's how they differentiate and don't mix them up. You don't want to start adding, numbers together that don't go together. So they use this idea. So we're going to be playing with this and graphing. You won't be graphing the complex like you see here, but I just want you to understand that there's an actual physical meaning to it. And we're just going to be doing the basics with it. So let's look a little bit at that, and let's see where you're going to use it. Okay, so here's a basic equation that you guys know how to solve, and where you run into these imaginary numbers, like you'll see one right here. Right, has to do with taking square roots of negative numbers. So a square root of negative is synonymous with imaginary. Whenever you take square roots of negatives, you get these imaginary numbers. So we take the square root of both sides like we normally would, and normally we'd say, stop, we cannot take a square root of negative, there's no way. Okay. So to get around this, and to be able to actually calculate that power flow in two directions, here's what we do. We just separate this into root 25 times root negative 1. That way we can still take the square root of 25. The problem is the negative, so since that's the problem, get it out of there. And since negative 25 is 25 times negative 1, we're okay. Now we can take the square root of the 25, that's 5, and we'll always have this negative square root of a negative 1 left over everywhere. So instead of saying 5 square root of negative 1, we use the abbreviation I. So anywhere we get this square root of negative 1, we'll use an I instead. By the way, what did I miss here? Did I catch it? Yeah. So if I take the square root of both sides, what happens? I actually get a plus or a minus. Plus or minus. Plus or minus. So remember, based upon that graph, whenever we get these roots here, we have to get 2 of them. Because it's like a mirror image. So getting only one imaginary root is like looking in the mirror and not seeing yourself. Basically what it is. You have to have a pair. You have to have the original, you have to have the reflection, you can't have just one. So you always have 2. Okay, so keep that in mind. At the very end, if you only see just one thing, if you don't see that plus or minus, okay, something's up. Okay? Just the idea of it says we have to have 2 of them. It's kind of like a starting and ending point. Okay. All right. So another one very similar. Let's just make one up. Let's say 8 x squared plus. What's a good number here? 64. Okay. Equal to 0. Negative 64. Divide both sides by 8. Negative 8. Square root. Square root. All right. So this is going to equal, we're going to say radical 8, right, times radical negative 1. Radical 8 equals, you might remember this, we have to break it up. That's radical 4 times radical 2. How do I know to do 4 and 2? That first number has to be a perfect square. It has to be 4, 9, 16, 25, 36, 49. The other number does not matter what it is, but that first number has to be a perfect square. So I have 2 root 2, and then finally I can change this square root of negative 1 to an I. And this format, the I, we're going to put it like this, 2I root 2. And then, of course, good. All this, really we should have had, as soon as we took the square root, we had 2 answers. So at the end, again, if you ever see an I answer by itself, and it's an equation, like we solve something, something's up. Okay, they only come in pairs. You got the image and its reflection, gotta have both. Good, good, good. All right. So there's some basic algebra in here. I mean, we have to know how to reduce that root 8. Just, rewriting the answer so it makes sense. Just put the I right here. It's an imaginary number. Good. All right. Now, believe it or not, this is about as difficult as we're going to go today. Okay. We're also going to do some stuff with adding, subtracting. Yeah, adding, subtracting. So let's actually get started. Yeah, I'm going to remind you about something called the conjugate. You don't need to write this down, but we're going to do a few of them together. Yeah. I'm going to remind you about something called the conjugate, where we don't want any i's in the denominator ever. So we're going to multiply by 3 minus 5i on the top and bottom. We're going to have other problems that just have like maybe 2 over 4i. We're going to multiply those by I on the top and bottom. We'll see why in a minute. Okay, so we're going to do a lot of this little tiny works, little few steps here and there, and nothing more than that. And then a few solving at the end. I'm just going to pass out your homework. We'll do a few, let you work, and go back and forth. Okay. All right. So recall that since I equals the square root of negative 1, if we see something that's like 2 over 3i, that really means 2 over 3 times the square root of negative 1. And we have this old rule about not having radicals in denominator. So seeing the I in the denominator is the same as a radical in the denominator. Okay. So to remedy that, you might recall, how do we get rid of a radical in the denominator? It's that you multiply it by itself. Okay. When you multiply it by itself, it cancels out. So we'll have 2 times the square root of negative 1 over 3 times, and what does this equal? Radical negative 1 times radical negative 1 just equals the negative 1. The radicals cancel out. And that was our whole goal from the beginning, is cancel out radicals. So our final answer would be something like this. No more radicals in denominator. But of course, this whole problem is not what you would see, because instead of writing square root of negative 1, we use I. So this whole problem can be rewritten as 2 over 3i And then instead of multiplying by root square root of 1 over root square, we would do just I over I. And that would equal 2I over 3 times negative 1. So notice that I times I is equal to negative 1 because of square root of negative 1 times square root of negative 1. It's the same exact thing. So we get 2I over negative 3. Okay, so same thing, but instead of writing the root negative 1 over and over, we'll use I instead. It's just abbreviation to cut down on the redundancy. Okay, so big idea, if I equals square root of negative 1, I squared equals negative 1. And this is powerful because it eliminates the I in the denominator whenever we need it. Okay. Now, I showed you earlier up here that that doesn't really work here. If I just multiplied by 5I here, we would run into a problem. So if I use the same idea and I said, I'm just going to multiply by 5I here, sure, that would cancel out the I on this one, because these two i's would now equal negative 1. Every pair of i's is negative 1. But then when I multiply it here, it'd create a new imaginary number, and I'd still be stuck with an imaginary number in the denominator. So instead of just multiplying by just the imaginary part, like over here, there's an I on the bottom, I multiply just by I have to multiply by this same idea, you just change the sign, and that cancels out the imaginary, and we'll do that right now. So let's look at the homework a little bit. I'm going to go down some of these odds with you, just give you a taste of it. So when we have positive, that really negates the need for parentheses in the first place. Because a positive times 4 is just positive 4. A positive times negative 4i is just negative 4i. It's just the same thing without the parentheses when there's a positive. In that case, that's called the real part. And we know that this is the imaginary part. We'll just add the reals together. Negative 5 plus 4. Get negative 1. And then negative 8i, negative 4i, and we get negative 12i. So here's where you see that you're measuring both directions. You're measuring the power going in and the power going out because we have two types of numbers. So we have a real part, and this is called the imaginary part. Okay. Together, whenever we get two different kinds of numbers together, we call that complex. It's a complex number. Okay. So just understand, we have imaginary numbers, and then when we have them combined with just regular numbers or real numbers, together they're called a complex number. Complex or compound, when you join two together. Alright, good. More of the same. Let's just keep going. This time you see there's a negative. So we got negative 4 minus 6i. It doesn't change, but now when we distribute the negative, we get plus 7 minus 3i. And you can mentally do this, or if you want to, you can underline, but just think about what combines together. So we have negative 4 and positive 7, that's the real part. What does that equal? 3? Yeah. And then negative 6i and negative 3i, that's negative 9i. That's just basic addition, subtraction. Just keep reals with reals, imaginaries with imaginaries, and it's pretty good. That's it for the adding, subtracting, yeah. Okay. So then we're going to do multiplying and then dividing. So we're doing adding, subtracting, multiplying, dividing, just so we know how to do all the operations with imaginary numbers. There's more addition. Now we get to 7, that's multiplication. So here's where you can do the FOIL, you can do the box, you can do whatever method that works for you, that you'd like. I prefer, just to start off, I don't know. What do you guys prefer? Box? FOIL? FOIL? Okay. It's the same exact thing, just one is written slightly different. Okay. So FOIL. First, multiply those. What does that equal? Yeah. And then what comes after F? Outside, so -5 times 6i is -30i. Inside, we got -8i and 3i. That's -24i. And then last, -8i and +6i. That's what? -48i squared. And instead of writing I squared, what should you write? -1. So you never really see an I squared in the problem. Anytime you come across the I squared, just change it to -1, and now you know, okay, the -15 and the +48 will go together, and then the imaginary parts go together. It's much clearer if we just change I squareds to -1 and never see it on our paper. Alright, so we have -15 plus 48. What is that? 33. Is that correct? 33, okay. Positive or negative? Positive, okay. And then -30 and -24? -54i. Yep, that's good. Okay. So yeah, big idea here is, yeah, I squared equals -1. Don't leave I squareds when you're doing your work. Just change them to -1s right when they happen. Just remember that if you see something like this, like 8 and 11, when it's written like this, just remember it's the same thing as this. It's just the same binomial twice. So if you're going to do the FOIL, just write the same thing again and do that. Do it that way. Now, if you like the box method, you'll see the same exact answer. That's fine. Whichever one works for you, you'll get the same answer. Going down to 13. What? So, mission here is always to get rid of the radicals in the denominator. I is a radical. So, multiply it by the same radical. So we get -4i over 9 times what? -1. Yeah, so the I squareds, always just replace it with -1. Simplify as needed. Sometimes the top number, bottom number reduce, sometimes not. Does anything reduce here? What reduces here, actually? The negatives, yeah. So we have, there we go. Yeah. Not too bad, right? Handle that. Go down. If we have like a binomial on top, we're just going to make sure we put parentheses because we're going to do the same thing but then end up distributing on the top. So I over I, or radical root 1, radical negative 1, radical negative 1, right? So the top we're going to get 2i minus 10, and then what should I put? I times I, negative 1. And on the bottom, I'll have negative 6, I times I, negative 1. So the negative 1's come from the two I squareds. And then just simplify as needed. So the top will now be 2i plus 10. The bottom will now be 6. Okay. See, does that reduce more? Yeah. So you can see a 2 goes into all of these, right? So make sure you reduce all of them by a factor of 2. It's kind of like distributing. We have to divide everything by 2. Okay. So we have 2 goes into here, we'll have just I. 2 goes into here, we'll have just 5. 2 goes into the bottom 3 times. Good. And so, little review. The real and the imaginary together is called a complex. We add, subtract just like normal. Okay, but just keep the real numbers together and imaginaries together. Never mix them up, because after all, these are radicals. So if we had a bunch of radicals and real numbers, we would not mix them up. We can FOIL or use the box method if we're multiplying. When it comes to dividing, no imaginaries left in the denominator, no matter what. In order to do that, just multiply it by I, and that cancels it out, because I squared equals negative 1, and that's not an imaginary number anymore. Okay, and I mentioned earlier, once we get here and you have a binomial on the bottom, don't write this down, but if we try to do this, like what we did right above, we'll get 10i, but on the bottom we'll end up with I minus 8. The minus comes from the I squared. So our whole goal was to get rid of the I, so we got rid of this I, but by multiplying just by I had to distribute, and I still have I. So the whole method that we did before does not work when you have a binomial on the bottom. It doesn't work that way. So we need a better method that actually for sure cancels out an I for both of them. It cancels out the I and does not create another one. So the trick for that is just to change the sign. And it's called the conjugate, multiply by the conjugate. So this is a very specific need. You have to know when to do this. Most of the time it's just this easy part, like up here, multiplying by I over I. So ask yourself, could you say in words or out loud, when are you supposed to do this when you change the sign? Okay. Okay. You have to know when to use this. You don't use it all the time, but you have to know when to use it. Alright, so let's do this. The top is just distributive property. 10 minus, what is that, 80? And we don't care about the I in the top, in the numerator. That's okay. On the bottom, now this is simply now one of these. The denominator is one of these problems, so you get a little more practice. You have to FOIL. 2 binomials, right? We have to FOIL this. So it's like a problem within a problem. However, you might recognize this as something like a difference of squares where there's no middle term. So when we had like x minus 2 and actually x plus 2 times x minus 2, you might remember that just equals x squared minus 4. We don't really have to FOIL this because we know the middle, that's going to be negative 2, that's going to be positive 2, you get 0. So instead of doing the normal FOILing, we just really have to do the first and the last. X squared minus 4, x squared minus 4. So same idea here. We're not going to go through all the FOIL because we picked certain numbers on purpose. Because we picked the same thing with a different sign, we only have to do these. So 1 times 1 is just 1. 8 times negative 8 is negative 64. And then I times I is negative 1. So as you can see, this does get rid of the i's and fixes our problem that we're trying to do. We're trying to get rid of the i's in the denominator, and that's what it did. So just simplify it a little bit more. And just like the one above it, look at all three numbers. Can they all divide by the same thing? Yeah, 5. So one more step. So divide by 5, 2. Divide by 5, you get 16. Divide by 5, you get 13. All right, and the last problems are kind of like the warm-ups that we just did. First thing, square root both sides, x equals plus or minus, and so on. Okay.